Myself Punyamurthy from Department of Chemistry, IIT Guwahati. I welcome you to IIT PAL program. In this class, we will study about alkanes. The last class we have seen about the structure and bonding, isomerism, nomenclature of alkanes, and in this class we will study about physical properties, chemical properties, and conformational analysis of alkanes. The first four members of alkanes are methane, ethane, propane, butane. They are gases. The next 13 members, C5 to C17, alkanes that contain C5 to C17 carbons, they are liquids. And alkanes that contain 18 or more than 18 carbon atoms, wax like solids. So, the first four members of this family, a series is gas, they are at room temperature, and the next 13 alkanes, alkanes that contain C5 to C17 carbon atoms, they are liquids, and the alkanes that contain more than C18 carbon atoms, they are solids. So, if you look at for example, ethane or any alkane, so the electronegativity of carbon is 2.6 and hydrogen is 2.1. So, is nonpolar strong, and this also almost nonpolar and strong. So, alkanes are almost nonpolar compounds. They dissolve only in nonpolar soluble like benzene, carbon tetrachloride. They are insoluble in water. So, alkanes are hydrophobic in nature, they are soluble only in nonpolar solvents and insoluble in polar solvent like water. So, if you go for boiling points, let us take compare butane and pentane and hexane. Let us compare the boiling point of this linear alkanes. This just we have seen, this is at room temperature is gas 0 degree. Boiling point of this is 0 degree. This is 36 degree centigrade, the boiling point of this one. Hexane is about 68 degree, 68.7 degrees Celsius. So, if you increase the molecular weight, if the alkanes are linear, increase the molecular weight. If you comparing this has 4 carbon atoms, this has 5 carbon atoms, we increase 15, right, carbon 12 and 3 15, increase the molecular weight, the boiling point increases. And if we increase further in this next comolar series, one more carbon atom, the boiling point increases to 68.7 degrees Celsius. Therefore, the boiling point increases with increase of molecular weight. This is because the intermolecular forces between the alkanes increases. When you increase the molecular weight, the surface area is more, and this because of van der Waals forces between the molecules increases when you have the longer chain and they have more surface area. Now, if let us compare the if you have the linear alkanes, if you increase the molecular weight, the boiling point increases. Now, let us compare the boiling points between isomers. Let us take this pentane. So, the linear one has 30 degrees Celsius and the other two isomers this is 2-methyl butane, the other one is this is 2, 2 dimethyl propane. If you compare the boiling point, and this is this about this boiling point of this is 28 degree Celsius, this one is 9.5 degree Celsius. So, you compare this all are structural isomers of pentane. This is a linear one, it is a branched one. You have one substituent in this case, then the boiling point decreases to 28 degrees Celsius, 36 to 28, about decreases 8 degrees Celsius. When you increase the branches, this is it has 2 methyl group substituent, and in this case the boiling point further decreases to 9.5. This is because the molecule is now compact, smaller in size comparing to that. The surface area is reduced. If the intermolecular forces decreases in this case, that is responsible. When you have branches, the boiling point decreases, that when you compare with the linear alkanes. So, just we have seen the physical properties of alkanes, where we have seen whether they are gas or solid, liquid at room temperature, and then non-polar character of alkanes. Then we have seen the boiling points. They are also colorless and odorless. Now, let us go for the chemical properties of alkanes. And just I have shown you, and the electronegativity difference between carbon and hydrogen is very less. They are almost non-polar molecules, and so the electron distribution between this carbon equally distributed. The two electrons, the bonding electrons is equally distributed between these two carbon atoms, therefore, is right. And similarly, here also this almost non-polar, the electron density between this hydrogen carbon is equally distributed. Therefore, the polar reagent cannot react at normal temperature, room temperature, they do not react, in other words, do not react with acid, base, oxidizing reducing agent, because of the non-polar character as well as the strong bonding between the carbon hydrogen. However, under a high temperature, and they can undergo some kind of chemical reactions. We are going to discuss those reactions next, and they can undergo two types of reactions. One is substitution reactions. Another one is thermal and catalytic reactions. So, we will see two types of reactions. Thermal means when you heat, burn in a high temperature, they can undergo degradation. We will see some of which are very useful reactions, and also there are some reactions when we use catalyst, then they can undergo reactions. First, let us see the substitution reactions. So, when you have alkane, for example, methane, you can replace the hydrogen with for example, halogen, nitro group, sulfonyl group. Halogen, it can be fluorine, chlorine or bromine or iodine. You can replace one of the hydrogen with halogen, or you can also introduce, you can replace with nitro group and sulfonyl group. So, this is called substitution reactions. Let us take, so these reactions are effective at high temperature, about 500, more than 500 degrees Celsius. Let us take the halogenized reaction as example, try to understand mechanism of this reaction. When you treat methane with, for example, halogen, let us take chlorine. At higher temperature, above 500 degrees Celsius, or UV light, when you expose to UV light or higher temperature, they can convert into chloromethane and HCl. This can also undergo further reaction with the chlorine, and it can get a dichloromethane, then trichloromethane, tetrachloromethane. Basically, you will end up with a mixture of compounds, chlorinated compounds, where when you heat at high temperature or UV visible light. Is an example for substitution reaction. What happens here? One of the hydrogen is replaced by the chlorine substitution, and we generate HCl as byproduct. If you compare the reactivity of halogens with methane, and this is the reactivity order of fluorine is very reactive, then chlorine, then bromine, then iodine. So, if you compare the reactivity of hydrogen, this is primary hydrogen, methane, and you can also have tertiary, secondary hydrogen atoms, and tertiary hydrogen is more reactive comparing to the primary, secondary is more reactive comparing to the primary hydrogen atoms. This is the reactivity order of halogens towards alkane, and this is the reactivity order of hydrogens towards halogen. If primary, tertiary hydrogen, it will more reactive compared to secondary is more reactive comparing to the primary hydrogen atoms. And if you compare this reaction of with the fluorine is very reactive, very difficult to control, very reactive, but chlorine we can control. Of course, you will end up with a mixture of compounds, and bromine is very slow. When you go for iodine, and you can react, but the reaction is reversible. And before going to that, let us see the mechanism of this reaction, then we will see the iodine reaction. So, mechanism. It involves 3 steps. First, what happens to the chlorine? This is called initiation step. The chlorine undergoes homolysis when you expose to light or heat, UV light, and you generate chlorine radical. It involves a free radical process. This chlorine bond can undergo homolysis to generate 2 chlorine radical. This is called initiation step. Once if you form the chlorine radical can react with the CH bond, and this is called propagation step. And the chlorine radical, now you have the CH3 . So, now the chlorine radical can react with the CH bond. So, you will end up with CH3 dot plus HCl. So, chlorine radical reacts with methane, you produce now methyl radical and HCl. So, this methyl radical can react with chlorine. You will generate chloromethane and Cl dot. So, the methyl radical can react with the chlorine, you produce chloromethane and chlorine radical. These two steps, this and this will go on until you have the reactant in your flask. This called this step, this and this can repeat and go on like this, and you will produce until you have the reactant. Once the reactant is consumed, and what can happen, these two radicals can combine together, can generate a neutral molecule. For example, this is called termination step. So, you have the chlorine radical, these two chlorine radical can combine together, you generate again Cl2 chlorine. Methyl radical, you have two methyl radical can combine together, you can generate ethane. Or chlorine radical, you have this can react with methyl radical, you generate. So, this is called termination step. Basically, free radical reaction involves three steps: chain initiation, where you generate a radical. Now, of course, different methods are available. You can use light, heat and peroxides like to initiate the reactions. Once you form the radical, this radical can react with your substrate alkane, and you generate alkyl radical. The alkyl radical further react with your halogen and generate corresponding alkyl halide. So, once the alkane is consumed, the free radical can combine together, and then you generate covalent molecules. This is about the mechanism of the halogenation of alkanes. So, just we have seen the formation of chloromethane. The chloromethane also can further react with the halogen. You get similar way dichloromethane, trichloromethane and tetrachloromethane. Basically, you will end up with mixture of halogenated alkanes. And I mentioned that when you react with iodine, the reaction is reversible. To push forward the reaction, what we can do when we add extra oxidizing agent in this reaction, for example, HiO3. So, this can be now converted into I2 and water. So, when you add this oxidizing agent, the reaction can be carried out, the iodination can be carried out. If you do not add the oxidizing agent, and the reaction is reversible and the reaction can stop, as you can see here. However, when you add this one, the reaction can be perceived, you get the iodomethane. So far, we have seen the halogenation of alkanes. Now, let us go for the next reaction, oxidation. They can be broadly divided into two groups: compustion. In this, what happens when you ignite, for example, methane, it be converted into, in the presence of excess oxygen, it can be converted into carbon dioxide, water plus heat. So, when you ignite alkane, the excess of oxygen, you generate carbon dioxide flame, and water is a byproduct, you produce heat. So, this is the basis of what we use alkanes as a fuel, and you can generate a lot of heat for production of power, and we burn when you ignite alkanes, and you can produce a lot of heat. And the general equation for the combustion reaction is CnH2n plus to this alkanes, and it when you 3n plus 1 by 2 is oxygen, and gives n CO2 and n plus 1 H2O plus heat. This is the general equation used for combustion reaction. In this case, methane carbon is 1 and 1 and 4 by 2, and this is going to be oxygen. And this is the equation, and in this case is going to be 2 oxygen, and carbon dioxide is going to be 1, and the n plus 1 and 2 molecule of water, and they produce heat. So, this case completely the alkanes ignited, and if you do not have sufficient oxygen, and if you have less amount of oxygen, and the reaction stops, and you produce carbon and water. So, if you do not have sufficient amount of oxygen, and the reaction stops and produces carbon and water, and the carbon we use for various applications, for filtration as well as for making ink and for cartridges. Next, partial oxidation. And in the presence of catalyst, and alkanes can be oxidized to, for example, methane can be oxidized in the presence of molybdenum oxide. It can be oxidized to aldehyde, formaldehyde. This is partial oxidation or controlled oxidation. So, alkane can be oxidized to formaldehyde. Similarly, if you have ethane, ethane can be oxidized in the presence of manganese acetate to acetic acid or ethanoic acid. It can be oxidized. These are called controlled oxidation. So, alkanes also can be oxidized. There are now so many modern methods is available to oxidize alkane to alcohols, aldehydes, carboxylic acids. The next reaction is isomerization. So, for example, butane. When you treat linear alkanes with anhydrous aluminum chloride in the presence of HCl gas, they can undergo isomerization to give two-methyl propane. This reaction can be carried out at room temperature. So, when you treat N alkanes with anhydrous aluminum chloride in the presence of HCl gas, they can undergo isomerization to produce branched alkanes. This is called isomerization reactions. Of course, you will get mixture of compounds. This is the major product. And similarly, instead of butane, when you react with pentane, so you will get 2-methyl butane plus two dimethyl propane. You will get mixture of more compounds. So, these are two major compounds, and basically the alkanes can undergo isomerization to give 2-methyl butane and 2,2-dimethyl propane and other byproducts. So, these are called isomerization reactions. This reaction can be easily performed using, as I mentioned earlier, using anhydrous aluminum chloride and dry HCl gas. The next reaction is aromatization or forming reactions. N alkanes having more than 6 carbon atoms, when you treat the alkane at higher temperature and pressure, and they can undergo cyclization followed by dehydrogenation to give aromatic compounds. For example, when you react N-hexane at higher temperature around 700 degrees Celsius, when you heat at high temperature in the presence of under 10 to 15 atmosphere pressure, in the presence of, for example, chromium trioxide alumina catalyst, and it can undergo dehydrogenation followed by cyclization to give benzene in this case. A hydrogen gas. Similarly, instead of hexane, if you have heptane, you can make toluene. If you have octane, you can make ethyl benzene and so on using different catalysts. This is called aromatization reaction. The next example is a reaction with the steam. When you react alkane in the absence of air at higher temperature in the presence of nickel catalyst, for example, methane, when you heat at higher temperature in the presence of nickel about 1000 degrees Celsius at higher temperature, they can convert into, if you do not have the absence of air, they can convert into carbon monoxide plus hydrogen gas. So, this is the process industry use to make hydrogen gas. So, the reaction here, when you treat alkane with the steam at higher temperature, the presence of catalyst and the absence of air, that is very important. You produce carbon monoxide and hydrogen gas. This is industry used to prepare hydrogen molecules, hydrogen gas. The next reaction is pyrolysis of alkanes. This also is called cracking, and the higher alkanes can be cleavage into smaller molecules, which can find broad utilities as fuels and for other applications. For example, let us take ethane. When you heat ethane at higher temperature, at 500 degrees Celsius, the absence of air, it can undergo pyrolysis to give ethylene, methane, hydrogen gas. So, when you heat at higher temperature, the absence of air, it can undergo cleavage to give a mixture of ethylene, methane, in this case hydrogen gas. So, this reaction takes place via free radical pathway. What happens? As we have seen the case of chlorination, this also involves 3 steps. Initiation step. So, the ethane can undergo homolysis to give 2 methyl radical under heating at 500 degree or higher temperature. You generate 2 methyl radical. This is the initiation step. Once you form this one, the methyl radical can react with another molecule of ethane can generate methane plus ethyl radical. First, the ethane undergoes homolysis at higher temperature to give 2 methyl radical. This methyl radical now reacts with the CH bond of this ethane, you generate methane plus ethyl radical. This is called propagation step, this initiation step, where you generate the radicals. Once you form the ethyl radical, this ethyl radical can undergo cleavage as shown here to give ethylene, a carbon-carbon double bond plus hydrogen radical. This hydrogen radical now react with ethane you produce H2 plus ethyl radical. This can go on like this, a repetition of these steps. This is called the propagation of the reaction. So, this radical, 2 radicals also can combine once, as I mentioned earlier, once the substrate is consumed. So, these 2 radicals can combine together, the reaction can be stopped. This is called termination reaction, termination step. So, the 2 hydrogen radical combine together, you get hydrogen molecule, and similarly 2 ethyl radical can combine together Higher alkane, of course, this can undergo further reaction and it can be converted into ethylene and methane. So, basically what happens in this case, and the overall if you look at the reaction, I wrote the ethane can be converted into ethylene, methane, hydrogen gas. You can see here how the methane forms, how the ethylene forms, how the hydrogen forms. So, this is a very important process. For example, let us go for the other example, dodecane. So, dodecane is a main component of kerosene. When you heat dodecane in the presence of platinum, palladium, nickel catalyst at around 700 degrees Celsius, they can undergo cleavage to give a mixture of heptane and pentane. Smaller fractions, other hydrocarbons. So, this is called cracking of hydrocarbons. This is very important process to make fuels. Now, let us see the conformation analysis of alkanes. In alkanes, the carbon-carbon single bond can undergo rotation that can give a different spatial arrangement of atoms in space, that is called conformational isomers. For example, let us start with ethane. So, this is ethane, and if you look at from this side, we can see here this carbon is bonded with 3 hydrogen atoms, and behind the next carbon also is bonded with 3 hydrogen atoms, say exactly behind this one. You can see from here, and this can have one structure, and due to the single bond rotation, this can undergo single bond rotation. You can have different spatial arrangement of atoms, and you can have here in this, if you look at from this side, you have the CH bond in between these 2 CH bonds. And if you compare these two, in this case the CH bond just behind to that, and here the CH bond is in between these 2 CH bonds due to the carbon-carbon single bond rotation. These two are called conformers or rotamers and or conformational isomers. So, let me draw the Sahar's and Newman projection of ethane. This is a Sahar's projection. So, whatever the structure I show you is this one. You look at it, this one, if you look from this side, and this hydrogen is exactly behind to that, and this is called eclipse conformation. And this one, if you look at it, this due to rotations of this group, there is a different spatial arrangement of these atoms in space. and this is the extreme case, and this is called staggered conformation. This is the Sawhorse projection of ethane. This is a Newman projection of so this is the front side carbon, this is the rear carbon, and you can look at it this one. This is the for eclipse conformation. This is a staggered conformation. These two are called conformational isomers or different conformations, and if you look this one, look at this one, this is just behind there is a repulsion between this bond pair, this bond pair. So, therefore, this conformer has more energy, potential energy comparing to that. In other words, this is less stable, about 2.8 kilocalories per mole. So, due to the repulsion between these two bond pairs, and it has more energy, potential energy comparing to that. In this case, and so this CH bond is in between these two one. There is a less interaction between the bond pairs if you compare this eclipse conformation. And this exactly you can see here also, this is the eclipse conformation, this is staggered conformation, and the difference between these two. So, is for example, in this case this got dihedral angle. These two are extreme cases, right. This is the more sterically hindered one, and this is due to the bond repulsion between, this is called torsional strain. So, due to the bond repulsion, and it has more potential energy, and if you compare the other one, this extreme case, this has is more stable one, and comparing to that, these two are extreme cases. In between there are so many infinite conformations available, and those are called skew conformations. For example, here the dihedral angle is 0, here the dihedral angle is maybe 5 to 10, right. This is called skew conformation in between, this extreme case. This eclipse one extreme case, this is the staggered one, is more stable, less stable, in between whatever the conformations are available, these are called skew conformations. Now, let us see the energy level diagram, and if you see, look at it this one, and so that room temperature due to collision, and that they get potential energy about 15 to 20 kilocalories per mole. So, there is no problem. So, room temperature they can readily undergo, because the energy difference between these two conformations is about only 2.8 kilocalories, they can readily undergo rotation to have infinity number of conformations. And if you look at the energy level diagram of these two extreme conformations, so potential energy, rotation. So, this is the energy level of the staggered conformation. Of ethane This is a staggered conformation. This is the eclipsed conformation. This again staggered conformation. So, in between whatever the energy is, the gap between these two is about 2.8 kilocalories per mole. In other words, this staggered conformation about 2.8 kilocalories more stable comparing to this. And whatever the conformations we have in between, those are called skew conformations. For example, so let us summarize now, and so alkanes can readily undergo carbon-carbon single bond free rotation that can lead to the different spatial arrangement of atoms in space, and those are called conformational isomers or conformers or rotamers. And if you compare these two, if you take ethane, and these are the two extreme conformations. This is the less stable due to the torsional strain, and this is the most stable. And in between there are so many conformations possible, and those are called skew conformation. And when you can go on like this, for if you want this about ethane, if you go for propane, and this will be the eclipse conformation, and this will be the staggered conformation for propane. And for butane, this will be the staggered conformation, and there are this will be the this, and these two will be the eclipse conformation. These are less stable comparing to this. You can go on like this. Let us summarize today. We have seen the physical properties of alkanes, then we have seen the chemical properties where we have seen the substitution reaction, then thermal and catalytic reactions where we have seen oxidation reactions, complete oxidation of alkane to carbon dioxide and water where we generate a lot of heat, which is the basic and fundamental process for using hydrocarbons as a fuel. Then we also have seen fossil oxidation reactions, the presence of catalyst at appropriate temperature, the alkane can be oxidized to aldehyde or alcohols. Then we have seen isomerization reactions, and alkanes, linear alkanes can be converted into branched alkanes isomers using anhydrous aluminum chloride, the presence of dry HCl gas. Then we have seen aromatization reactions. When you have linear alkanes that contains more than C6 carbon atoms, when you treat these alkanes at high temperature under pressure with catalysts like chromium trioxide supported alumina, they can undergo dehydrogenation followed by cyclization to give aromatic compounds. Then we have seen a reaction with the steam where what you can do in the absence of air, and the present nickel catalyst, alkanes can be converted into carbon monoxide and hydrogen gas. This industrial process we use to generate hydrogen gas. Then we have seen pyrolysis, very important reaction. The higher hydrocarbons can be cracked into smaller molecules that we use as fuels, and we have seen one example, for example, how you can convert ethane into ethylene and methane and hydrogen gas, and this reaction involves free radical pathway. And then we have seen one example how the main component of kerosene, dodecane can be converted into heptane and pentane and other smaller fractions easy in the presence of palladium platinum based catalyst at higher temperature. So, these reactions are performed in the absence of air, and then we have seen the conformation analysis, where due to the carbon carbon single bond rotation and the atoms can be arranged different way in space. These are called conformational isomers or conformers or rotamers, and they have infinite number of conformations, but if you go for extreme, and in the case of ethane we have seen, we can have two conformations. One is eclipse conformation, another one is staggered conformation. These two are extreme cases, and the energy difference between them is 2.8 kilocalories per mole. And in the case of eclipse conformation is less stable due to the torsional strain, and there is a repulsion between the bonding electrons, and they have less 2.8 kilocalories more energy than the staggered conformation, and in between whatever the conformations available, they are called skew conformations. We have seen two projections, one is staggered, one is Sawhorse and Newman projections. Similarly, we can also go on for other alkanes like propane and butane. So, with this I conclude this lecture. Thank you very much.